Besides looking at the end behavior of rational functions, we're also interested in some of the other ways rational functions can produce interesting behavior, in particular, discontinuities. Now, discontinuities in rational functions occur at a value which makes the denominator equal to zero. When we try to divide by zero, we get an undefined situation. And these undefined situations can take one of two forms on a graph. We can have a removable discontinuity, where we have a nice steady graph except for one place on the function, where the graph disappears, a single value of x. We can also have a place where the graph is undefined and it's shown by a vertical asymptote. So here we have one where at x equals 1 there is, got away from me there is no value of y because for some reason the expression doesn't allow us to compute one. So let's take a look at these two possibilities and what type of rational function will produce each of them. So let's start with a removable discontinuity. Here's an example of a removable discontinuity where the function is x squared minus 1 over x minus 1. Now here, if you plug in a value, let's try 2. We'd say f of x equals 2 squared minus 1 over 2 minus 1. So we have a nice number 4 minus 1 over 1, which is just 3. No problem. But if we try to plug in the value 1, we can see that we're going to have a problem here. F of x equals 1 squared minus 1 over 1 minus 1. And we get this unknown quantity 0 over 0. So at that point, otherwise we get a nice steady line. Now, the reason we know that it's going to be this whole is because it only occurs at this one value, and otherwise we see a nice steady trend in our values. To see it algebraically, we notice that the top here, x squared minus 1, can be factored to an x plus 1 times an x minus 1, the difference of squares. A plus b times a minus b gives me a squared minus b squared. And we divide that by x minus 1, and we can see that we have this common factor. And no matter what happens, we can write this as x plus 1 times the quantity x minus 1 over x minus 1, which is essentially 1. So what we're doing here is no matter what value for x we choose other than 1, this quantity is going to be equal to 1. 4 minus 1 over 4 minus 1, 2 minus 1 over... So essentially we're taking this line x plus 1 and multiplying it by 1 as long as x is not equal to 1. Which gives us the line over here, x plus 1, except at x minus 1. And there, since we're trying to divide by 0, we don't get a value, and we put in our whole. So anytime we have a factor that's in both the numerator and denominator, we're essentially multiplying the rest of the polynomial by a quantity of 1. The only time we're not multiplying by 1 is when that factor itself is equal to 0. Our other option is a vertical asymptote. And here, we look again when the denominator is equal to 0, but we see that in this case, this 2x minus 1 over x minus 1, there's no common factor to remove this problem at x minus 1. So it creates instead a vertical asymptote. And we examine its behavior as x gets closer and closer to the value that makes our denominator 0, or in this case 1. So let's plug this into our calculator. We're going to clear out this. We'll get 2x minus 1 over divided by the quantity x minus 1. There we go. And if we look at our graph, we'll see this behavior around x equals 1. Let's go back and sort of test out what's going on there. So if we looked at a number very close to the value x equals 1, but slightly more positive. So let's go for vars, y vars function, y1. Whoop. And we took a number just slightly larger than 2. So say like 2.1. Or actually 1.1. That's what we're really looking for. Number slightly larger than 1. And we see that we get a fairly large number, 12. And if we took something that's even closer to 1, but still slightly larger, so 0.01, whoop, 0.01, we get a number even larger. And that makes sense, because what we're doing here, if we go back and we look at our function, if I take 1.01 minus 1 in our denominator, and 2 times 1.01 minus 1 in our numerator, I get 2.02 minus 1, which is 1.02, but then I'm dividing by a really small number, 0.01. And dividing by a small number gets me a large number. And the smaller, or the closer I get to 1 for my x values, the larger my number will become, because I'm dividing by a smaller and smaller number. Let's take a look at what happens when x is slightly less than 1, so like 0.9. So let's go back up. And instead of 1.1, let's use 0.9. And we get, a minus 8. So a fairly negative number. So let's try something a little closer. Instead of 0.9, let's try 0.99. That's closer to 1, but still slightly less. And it gets even larger. We'll see that same trend as we plug in numbers closer and closer to 1. And we can see exactly that behavior from the graph. As x gets close to 1 from the left, we can see that our graph is diving down. And as x gets closer to 1 from the right, we see the graph growing more and more in a positive fashion. So one way of writing that using that new limit notation would be the limit as x approaches 1 from the positive side of my function would be positive infinity. Our graph gets more and more positive as x gets closer and closer to 1 from the positive side. We can also say that the limit as x approaches 1 from the negative side of our function would be negative infinity. Our graph gets more and more negative as we get closer and closer to 1 from the left, or the negative side. So let's do a quick recap. How do we determine the end behavior of a rational function? Well, we compare the degree of the numerator to the degree of the denominator. What are the possible end behaviors of a rational function? Well, if the degree of the numerator is less than the degree of the denominator, then we would say that the graph will eventually approach a horizontal asymptote of 0. If the degree of the numerator is equal to the degree of the denominator, then our graph will level off at a horizontal asymptote where y is equal to the ratio of the leading coefficients. So if n is less than d, then y approaches 0. If n is equal to d, then y approaches an asymptote formed by the leading coefficient over the leading coefficient. And finally, if n is greater than d, so the degree of the numerator is larger than the degree of the denominator, then our y function begins to approach a non-vertical asymptote, which is found by division of the denominator into the numerator. In addition, we looked at discontinuities. What causes a rational function to be undefined or discontinuous at a particular value of x? Well, it's when we divide by 0. So whenever the denominator is equal to 0, we'll have some sort of a discontinuity. The possible behaviors of the graph near these values which cause the denominator to be equal to 0 are either a removable discontinuity, or a vertical asymptote. Asymptote. Right? How do we determine which of these behaviors will occur at or near these values of x? Well, a removable discontinuity will have a common factor in both the numerator and denominator at that value where x will create a division by 0. Whereas a vertical asymptote, that factor will only occur in the denominator.